Okay, so let's talk about, again, I've defined all of these different types of standards, and we're going to go through each one, but mostly we're going to combine these ones together and talk a little bit more about them. We've touched on them again. So again, these international standards, certified standards, just available from NIST and IAEA, and we talked about the expense and that they take a long time to be able to try and do. So you can't get very many of them. And then here's a list for carbon. You can see that these are carbonates associated with them, and then you have a graphite. Oil and sucrose are the two biological materials, so they're very purified ones that they can be sure to be stable over time, so they don't have drift. They don't do things like ladybugs ground up or leaves or anything like that. So you have to make those ones yourself. So that's why we come into the working standards. And again, with the working standards, you're kind of working at trying to get a range of samples of different types of materials that also span from high and low in every type of measure that you would want to try and make. So for carbon, for nitrogen, for sulfur, for hydrogen, for oxygen. So all of these things to try and do. And it's pretty difficult to do, to find the highs and lows in all of these. This is what we end up doing. These are NIST certified samples, but they're samples certified for concentration. So they say percent nitrogen and percent carbon. Those are the ones you end up using to calibrate for the percent carbon. And then you can get an isotopic value. The nice thing about these, though, is that they've picked them to be consistent in that percent carbon, so they're finely ground, they're well homogenized, they're stable. They've all of those things that make them nice for percent carbon standards make them good for laboratory working standards to do. So we get isotopic values for those. And here's sort of our iso space with, we have carbon plotted here and nitrogen plotted here. And you can still see that while we have a pretty good coverage in here, we've got blank spaces. And it may be that there just aren't things that live out in those areas, but we're constantly on the hunt. Anytime you find yourself with something that has an unused, this was I think it was a seaweed that we brought in from the coast that ended up giving us a new part in space with high carbon and relatively high 15N. So that was a nice addition in. So we're constantly looking for those things to build this space. All right, we've talked a little about study standards, but here's a very nice paper, if you wanted to look at it, where they were doing this for tree ring processing. So when they're extracting the cellulose, they had their big bulk sample that they had worked up in wood, and they would just drop one of these samples in with every batch that they ran through to do cellulose extraction with. And then they could see whether or not something had gone wrong with a particular batch. Somebody left it on too long within the bleaching process or some other process, or they let the stuff dry out and they kind of got a little burnt. And I've seen that happen before. Did it make a difference? Did I ruin my samples or did I not? Well, if you had something like this, you could answer that. If you don't have something like this, you always have that question in your mind. And you just have to flag those ones in your data set, and then you have to think, well, did they look weird compared to everything else? But it's nice to have that if you can. Any more questions about these types of standards, particularly thinking about study standards, if you wanted, or could you do one for yours and how might it look? I mean, for gases, another one might be, just to go out to the field, you might take one of those little Scotty bottles that's a standard that has a known isotopic value with it, and you could fill up particular containers and then bring them back and look for, changes in the isotopic values for that.
That's a good idea.
Okay, the last topic we want to touch on is on how to select a good lab. How many of you are going to have to send away samples at some point in your career to somebody else and have them run them? At least, okay, maybe 67, yeah. Yeah. So Labs vary a lot in their quality assurance, quality control. There's a lot of labs who kind of say, what? I don't know what you're talking about when you say quality. Where's my quality assurance plan? I don't have one. I don't know what you're talking about. So they should have available for you some standard deviation, long-term data on their QC standards so that you can see how well they've been doing. Although often, I must admit, they get carried away. They don't keep track and they don't always write them up. So they kind of get it once and they'll look at them over time. They should be looking at them because it's a really good check to see whether or not they need to do maintenance to the machines or not. But things get overwhelming. You should ask them about their calibration and their QA process. A lot of them will just talk your ear off about it. Oh yeah, this is what we run and this is what we do, and they'll just, they'll go on and on and on, which is great. So then you've got a pretty good lab. You want to also find other people who've run samples there and ask them their opinion if you can. And then if you are sending things there, you want to make sure that they're sending you all the data. They're sending you back the standard data. They're sending you the replicates that they ran or duplicates from your samples. You may have your own duplicates from the field duplicates you ran in, but they will also duplicate samples usually for the analytical duplicates. And so you want to get all that data back from them so that you can do the calculations. Here's an example of variance. This is an IAEA round robin where they sent out 4 water samples to labs, and these are labs that signed up, so they volunteered. They said, yes, I would like to test my QA/QC. I know these samples are ones that I'm running for a test from IAEA, and I'm going to do the best job I possibly can to get those numbers right. And they measure them. So what this is the cumulative error on those 4 from the true value that they had. So, and they multiplied the value by 8 for the oxygen so that they could put it, this is a hydrogen scale. But you can see this is our lab here. For the most part, things are pretty good, but then when they start getting up above 10 per mil or so, you really start driven. But look at this end of things. This is a lab, they knew that they were in this round robin. This wasn't just somebody sneaking in some samples on them and testing them, right? This was, and they're off by 100 per mil.
To what you get?
To what all the rest of the labs, or in what the known value is. So cumulative over the 4 samples that they had was by 100 per mil off. But for 4 samples, okay, that's a lot. That's a lot. Almost all of this can be related to improper handling of the samples themselves. That they let their standards get evaporated.
Since voluntary, is this a report reason?
No, because it's voluntary, it's also meant by IAEA to be helpful to labs that want to be commercial laboratories or do other things, and they want to help them correct themselves into that they know how well they're doing. And so they work with these people to try and figure out what the problem is and help them correct the problems. So that was one of their main missions. So because of that, and because it's voluntary to get more people to do it, they don't reveal the identities. These are all little numbers on here. Yeah, these little teeny things are little numbers, and they're all, so that the numbers are available, but you don't know which lab is which.
I have to ask.
Yeah. Here's a case of really good quality assurance, quality control between labs. This is the national or the global CO2 monitoring network. There are 2 different laboratories here that measure the CO2 concentration and the isotopic ratio of flasks collected around the globe. These 2 labs had better be getting the same value, and they better get the same. So what they do is they have standard flasks that they mail back and forth to each other, and they take measurements on and they compare how they're doing over time. So you can see the range here, this 0.05, and most of their samples fall between that. So it's extremely good accuracy and precision. But this is the type of thing, this is part of their quality assurance plan, is that they can demonstrate to the world that the data you're getting when you look at those CO2 monitoring networks is good. And they're getting good quality work. This is our lab over time, what it might look like if you get sort of, this is a QA standard, the bovine liver from NIST, and a value that we get over time, and our accuracy, or the value we get and the precision that we have on that. So that's just something to get. But this isn't, again, something that you would report, because what if your samples were run on this day? Then the long-term average means nothing relative to what it is for your particular standards and your samples that came. So you have to pay attention to that. Also, switching labs in the middle of the study. If you were running, say, we were running SULFUR for one lab, and then a contract ran up and we had to renew for a different laboratory. This is before we started doing SULFUR at our laboratory. And the second lab came in, and we sent the same samples to them, and you could see that they were off from each other. At least it was linear, and we could come up with a correction. So the ones that were run at this lab, we could calibrate them all to the other lab. But we don't know which lab was right, because we didn't send in a certified standard. They had standards. They sent us all those things. Everything looked good. But this is the type of variance that can happen. At least it wasn't a giant cloud of points. If it had been a giant cloud of points, then one of the labs was giving us worthless data. Maybe they both were giving us worthless data if they were in a cloud. But if you have a relationship, then you could at least correct if you have to switch, from one lab to another. But this is a reason why not to switch laboratories. And this is common in the isotope world, particularly when you're getting at types of samples that are difficult to do, such as, say, nitrate in water or sulfur types of samples. Percent carbon, percent nitrogen, and carbon and nitrogen isotopes for those, that's a relatively routine, so most labs can do a pretty good job, but it's the other ones that are more of a problem. This is just to highlight the problem with inorganic or organic contamination associated with the lasers and measuring water. I don't know how many of you guys are familiar with the contamination problem associated with that. So you can't run leaf water or soil water on laser system still. They haven't fixed the problem. So you end up with bad numbers. So here's the first clue to me that this was a problem, is when we got our laser system in 2008. That was the first year we had it. These were the source waters that I was looking at. These are soil waters, and I forget exactly how they go now, but these were the source waters, and these were the trees that we were measuring. And then we got another value for a tree that was sitting somewhere way out here. It was like plus 52 on both ends of it. And it was like, okay, something is wrong here. So I brought it with me when I came to IsoCamp that summer, and I had them run it on their Picaro, I think they had, and they got minus 53 or something. It was also really whacked out numbers, but in the other direction. And then we ran it on the IRMS, and it gave what we might expect, falling into more of a normal range. So we knew we had a problem. And then that sort of all started in when people started discovering this more. And so Adam West, who was a postdoc here in this lab, came up with a couple of papers, but now there's at least a decision tree. They've got, the laser people are aware, they have a system that you can flag if they think there's an interference. So alcohols get absorbed as well in the, again, this one is not measuring mass, it's measuring absorption of the light that's shown through there. And so anything that absorbs is going to cause an a perturbance in their calculations of what the isotopic ratios are going to be. They're aware, they can flag it for you in some cases, but in other cases it may not be enough. And so you have to decide if you're going to be able to trust the laser or not, and there's some steps you can go through on these ones. But they still have not fixed it, so I caution you, if you're going to do it, to do some subset of your samples that you run on an IRMS to make sure that those values compare and you can demonstrate it. Otherwise, you probably are going to end up with problems in going through review. I certainly don't let papers through that have leaf water measured on a laser system. For those of you who might set up your own laser system, this is a paper that came out in 2014 by Len Wassenaar and various other folks from the IAEA and from USGS. They advocate using their LIMS program, which you can or cannot do, you can use, but it's for the processing, talking about that. But they talk about where to run the standards and some of those kind of things. So at least it's a basis, it's a place to start for some recommended quality assurance, quality control, and procedures for doing that. So I recommend that to look at if you've never done it. Quality assurance with your study design. So let's think about when you're writing up your plan and how you might think about what you're going to try and do, and come back to these three things. You've got your source variation, the process variation, and then those things might be varying temporally and spatially, and probably both. So your experimental design should have you collecting samples to be able to account for that or control for that. If you know what your source variation is, if you're going to control for it or you're going to measure it. Put it in there, try and figure that out. Again, collecting representative samples, being able to do that. You're better off also, I should say, collecting more samples than you think you might need, because you don't have to run them all. But if you didn't collect it, you can't go back. So err on the side of collecting more samples and then figure out what you might be able to afford to do later on. Always duplicating 1 out of every 10 or 20 of your samples.
That label.
Go ahead.
No, I just was reading ahead, the
Oh.
labeling thing at the bottom.
Ah, yes, that's a very important point, yes. All right, so, but in here, again, when you come back, you've done procedures here, a whole bunch of them. Don't just assume that if you just set it up in your lab that it's going to work. Test it, make sure that your system is working, do some things to be able to make sure. So test procedures and things you set up in your lab. Make sure you can calculate your own accuracy and precision. Again, getting all of these for within a particular one that you might end up rerunning a tray. You might do some blind duplication for them. Again, homogenizing your samples, consistent voltages. But this one here we'll spend a little bit of time on. And this is not having the error of when you've got some complex name on a bottle and somebody else has to type that into the mass spectrometer, and flipping 2 letters or numbers can make a huge difference in which one it was as far as the sample. Like north and south, you're using those, and they could be interchanged one way or the other. And these kinds of things cause so many problems, and it's an error that you could easily avoid if you made things a little more systematic and easier. If you're giving them samples, C, say for carbon, year, and then 1 through whatever number at the end, then you're pretty sure there's a lot of ways you can go through and check that they're not going to make a typo problem. And if they did, and you have 67, 68, 69, 96, or they switched it and they had typed in 96, you would see that immediately, right? You could catch that and be able to do it. But if it was north-south, south-north, or we had one where it was lysimeter or PNLS, and it could be PSLN, and they were 2 different places, a north plot, south lysimeter, south plot, north lysimeter, and they were constantly, I would look at those and I could not see the difference sometimes myself. And so it's a real problem sometimes. We switched them so that all lysimeters were just numbered 1 through 18, just simplify. The last point before we get into the exercise is that you guys should make sure to look at your data as soon as it comes back. Check all the QA, QC. Check to see that the values are in the range that you're expecting. Check it, compare it with previous samples you've done, moving through and doing this. Don't let it pile up, particularly if you're running your own samples and you get to be on the mass spectrometer only for a limited amount of time, and you're burning the midnight oil and you're getting the data off and you're just going to look at it later. And it piles up and piles up and piles up, and then finally you're all done, you're exhausted, and you go look at your data and it's like, oh no. We really should have done some maintenance. The machine was not working well, all this stuff, all the weighing that I did, all the midnight oil, it was a waste because the data was no good. And if you had just looked on that day one, you would have noticed the problem and could have got it fixed. Save yourself a lot of heartache. I can't tell you how many times I've just seen students crying because they ended up doing something like that and just let it get behind them, you know. So if you're weighing out all those samples, when that data comes back, look at it. Okay, so let's move on to the, oh, wait, last point, sorry. Coming back, and this is what we're going to go through each of these, but again, remembering that you want to be able to answer these. We're going to go through this exercise, and we're going to come through at the end of the exercise and be able to look at the data that we're going to calculate and how that helps us address these particular issues. Okay? So that's why we want to get done by 5. So we have 45 minutes to be able to try and get through this exercise, because at 5 o'clock, John's going to come in here and want to do it. And I want to be able to address these questions to make sure that you guys, when you set up your own studies and you have your own QA page for your study that's going to be similar to what this one is, you'll be able to calculate the information to answer these questions.